First problems we're going to do in this lesson is do some factor trees. I'm also going to show you a division ladder, but this is something we start teaching our students to do after they learn what a prime number is, and we start teaching them how to break these numbers down into a prime factorization. We're first going to look at a factor tree, and I'm going to give you a number, and it doesn't matter on a factor tree what factors you start with. So, for example, 240. We could start with 6 times 40, 80 times 3, 30 times 8, 2 times 120. It doesn't matter which two factors you start with. You just need to come up with two numbers that multiply to give you 120 and begin breaking that number down. So when we start, we don't all necessarily have to start with the same two factors, but we should all end with the same answer. So I'm going to start with the example, for example, with 6 times 40, because 6 times 40 does multiply to give us 240. And then these are both still composite numbers. And so what you're going to do is you're going to break these numbers down, factor them down until you reach prime numbers. So when I factor down 6, 6 is 2 times 3. And I like to circle once I hit primes to know that I'm finished with those, but they are still part of my answer. 40 is 2 times 20. 2 is a prime. 20, you can do 4 and 5 or 2 and 10. It doesn't matter. I'm going to go 2 and 10. And then 10 is 2 times 5. And this is probably a process that you've all already done before. But when you finish, I look at all the numbers that I have that are circled, and collectively multiplied back together, these would get us back to 240. This is the prime factorization of 240. When I write this prime factorization, I can count. I have a 2, 2, 2, 2. So that is 2 to the fourth, because that's what 2 to the fourth power is. 2 times 2 times 2 times 2 times 3 times 5. In the order in which you write those numbers does not matter. Just for organization purposes, I write them in numerical order. So that is the prime factorization of 240. You can also do what is called a division ladder. And when you do a division ladder, it's kind of like upside down division. But specifically when you do a division ladder, you have to divide by a prime number. And so that's where it's different than the factor tree. And so some people, might say, oh, divide by 10. No, because 10 is not a prime number. Or, divide by 4. No, 4 is not a prime number. Divide by 6. No, 6 is not a prime number. When you divide and use the division ladder, you have to divide by prime numbers. So I'm going to start with 2. 240 divided by 2 is 120. Divide that by 2 to get 60. Divide that by 2 to get 30. And notice I keep dividing by 2 because I know 2 is a prime number. And on the division ladder, you have to divide by numbers that are prime. 30, I'm going to divide by 3 to get 10. 10, I'll divide by 2 to get 5. And when I hit a prime number at the end, that's when I know that I am finished. And if I look at all of those numbers multiplied back together to give me 240, that's the same numbers that I ended up with in my factor tree. 4 2s, a 3, and a 5, which is 2 to the fourth times 3 times 5, will get me back to 240. The next number, number 2, I have is 864. And again, it doesn't matter how you start breaking down 864 on a factor tree. You just need any two numbers that multiply to give me 864. So I'm going to start with 4 times 216. And I don't circle either one of those because neither one of those are prime. I keep going in my factorization. 4 is 2 times 2, both of which are prime. 216, I'm going to do 2 times 108, even though that's not the only two numbers that multiply to give me 216. And 2 is another prime. 108 needs to continue to factor because it's composite. And so I'll do here 2 times 54. 54, I'm going to go with 6 times 9. 6 and 9 are both still composite, so I continue to factor to 2 times 3. Put the wrong number there. Both of now are prime, so I'll circle those. 9 is 3 times 3. Again, those are primes, and that's how I know I'm finished. I ended with all prime numbers. When I count up how many 2's are multiplied, I have 2 to the 5th power, 5 2's multiplied, and then 3 3's, so that's times 3 to the 3rd. Now again, I could also do this by a division ladder where I start with 864, but I have to divide by prime numbers. And so I generally stick with 2 and 3 if it's divisible by that, because it's just an easy way to roll with it. So if I divide by 2, that's going to give me 432. I can divide by 2 again to get the 216. I can divide by 2 again. Notice I keep dividing by a prime number to get 108. Can divide by 2 again to get 54. Can divide by 2 again to get 27. 27 is not divisible by 2, so I'm going to go 3 because I know that's prime, which is 9. Divide by 3, finally end with 3, and when you end with the prime number, you are to your answer. And if I look at what all gets multiplied back together to give me 864, it's the same factorization of 2 to the 5th times 3 to the 3rd. So these are the two boxed answers for the prime factorization of these two numbers. Now the next thing we have here is a theorem, and this theorem states, it's the fundamental theorem of arithmetic, and it says that each composite number can be written as the product of primes in one and only one way, except for the order of the prime factors in the product. And what this means in plain English is that it doesn't matter how we start. You know, we don't necessarily have to start the factor tree the same way. We do have to start with two numbers that multiply back to give us the original number. But what this is saying is, in a factor tree, we don't have to start the same way, but we should all end with the same product of primes. And the order in which we write those primes does not matter. So I prefer numerical order, but it is not wrong if you don't write your numbers in numerical order. I want to again refresh us on the exponent rules because we're going to do some prime factoring that does involve some exponents. And so just, remember when we multiply numbers that are the same base, we add the powers. So an example of that is if we have 3 to the 3rd times 3 to the 2nd, that is 3 to the 5th, because when you multiply, you keep the base and add the powers. The second rule, if you have a base to a power and it's raised to another power, then you multiply those two powers. And so power to power, we multiply. The next thing, if we have a parentheses, so let's say, I'm just going to do some variables here, x squared, y cubed, and the whole thing is to the 4th, what that means is that the x squared gets raised to the 4th, and the y cubed also gets raised to the 4th because the entire parentheses was raised to the 4th. We would then, continue this on power to power, we multiply. That would give us x to the 8th and y to the 12th. So just a refresher on your exponent rules, because as we move on to the next page of the notes, we're going to finish the second part of the lesson by doing these two examples where we do the prime factorization working with numbers that have exponents on them. So these are very simple, and I feel like sometimes people, tend to make these harder than they actually are. So when you look at this type of problem, and I'm asking you to do the prime factorization of numbers that involve exponents, what you first need to do is you need to prime factor the bases. So by bases, I mean these three numbers that I'm multiplying. So you can go off to the side if it's something you can't do in your head and say 14 is 2 times 7, both of which are prime numbers. And so you rewrite that base 14 as 2 times 7, but that 14 was raised to the 3rd power. And so you write 2 times 7 in parentheses and you cube that parentheses. 14 is a composite number, meaning we need to prime factor that base 14 because it's composite. 34, same thing. If I need to, prime factor 34, 34 is composite. That's 2 times 17, both are which prime? So this is times 2 times 17, and that's not raised to a power, besides the power of 1. So we're not going to write the power of 1 on that parentheses. 25 is not prime factor, so it's a composite number. I break it down as 5 times 5, which is 5 squared. 5 times 5 is 5 squared. So this is times 5 squared to the 9th power. And what I've done in step 1 here is I have rewritten this problem prime factoring all of these bases because they were all composite numbers. Then I follow through with the rules on the first page, the exponent rules. So if you have a parentheses to a power, each base in the parentheses gets raised to that power. So the 2 is cubed and the 7 is cubed, times the 2 times the 17. And then on this 5, the rule for power to power, if you look back to the previous page, is you multiply those powers, and so that becomes 5 to the 18th. This 2 is raised to the first, this 17 is raised to the first, just for reference. So now when I collect and multiply 2 cubed times 2 to the first, that's 2 to the fourth. And none of the other bases are alike, so I'm going to write times 5 to the 18th, times 7 to the third, times 17, which gives us our final answer. We have written this number that we started with in prime factorization because all of the numbers here that are multiplied now are bases that are prime numbers. Now I did put them in numerical order. That does not mean that you have to. You could write this in another order, like you could do 2 to the fourth times 7 to the third times 17 times 5 to the 18, and that 5 to the 18th, and that's still correct because the order in which you write your prime factorization does not matter. The next problem we're going to do in the exact same way. So the first thing, if we want to prime factor this number, the first thing we need to do is prime factor all these bases. So if I come over to the side, 100 I can say is 10 times 10, both of which are composite numbers. 10 is 2 times 5. Those are primes. 10 is 2 times 5. So 10 is 2 squared times 5 squared. So I come over here and I replace 100 with 2 squared times 5 squared. And the 100 was raised to the 15th power. So we raise that parentheses to the 15th power. Next number we need to prime factor is 64 because it's composite. That is 8 times 8, both composite numbers. 8 is 2 times 4, prime. 8 is 2 times 4, prime. That 2 is prime. 4 is 2 times 2, both prime numbers. 4 is 2 times 2, both prime numbers. We got a lot of 2's going on here. 1, 2, 3, 4, 5, 6. So 2 to the 6th power is 64 prime factored. So that's 2 to the 6th power, but that 64 was raised to the 12th power. So we raised that 2 to the 6th to the 12th power. Oh, my screen just went a bit crazy. I apologize. 15, if I prime factor it, is 3 times 5, both of which are prime numbers. So what I have now, 15, I'm going to erase the 64 so I have a good clean space. So that 15 is 3 times 5 to the 10th power. And if you look at this now, you've just all you've done is replaced with 100 with its prime factorization, 64 with its prime factorization, and 15 with its prime factorization. Then you have to have your knowledge of your exponent rules. So this first parentheses, we have a power to another power, like this power of 2 is raised to this power, and this power of 2 is raised to this power. And the rule on that, when you have power to another power, on the previous page, if you need to go look it up, is you multiply. So that's 2 to the 30th times 5 to the 30th. Same thing here on this 2, power to another power, you're going to multiply. So that's 2 to the 72nd power when you do 6 times 12. And then here, this 3 gets raised to the 10th, and this 5 gets raised to the 10th. Now you're going to combine like bases, so now when we do this operation of multiplication is when we add our exponents. So this is 2 to the 102nd power. When you add 30 and 72, you get 102. On the 5, you can do 30 and 10 is 5 to the 40th power. and then times that 3 to the 10th. And I purposely did not put this in numerical order because I wanted you to see from one of my examples that the order in which you write your prime factorization does not matter. It's just generally my personal preference to write them in numerical order. So you definitely are going to have problems like that on your homework and your test. And we're going to expand that just a little bit further on this number 2 here, where I say, is 5 to the 3rd times 7 to the 5th a factor of 5 to the 7th times 7 to the 11th? Explain why or why not. And if you recall from the last lesson that we did on divisibility, if B divides A, then recall we say B is a factor of A, and A is a multiple of B. So like a numerical example of that, remember, is 2 divides 12. 2 is a factor of 12. 12 is a multiple of 2. So that's the same thing even on these numbers that have exponents. So it is a factor of it if it's evenly divisible by it. And so if you recall, the rule for divisibility, it's a factor of it if we can multiply it by something to get the product. And the way that we check that is by doing the division. So if 5 to the 7th times 7 to the 11th is divisible evenly by 5 cubed times 7 to the 5th, then it is a factor of it. And we need to recall that when we do divide, we subtract our exponents. So this would be 5 to the 4th times 7 to the 6th power. And what we can say now is that 5 cubed times 7 to the 5th, if we multiply that by 5 to the 4th times 7 to the 6th, we do get 5 to the 7th times 7 to the 11th. So is it a factor? Yes, it is, by the definition of a factor, that we did in our last lesson. If we can take this factor and multiply it by another factor to get this product, then by definition, yes, it is a factor by the definition presented in lesson 4.1. Here I'm giving you a note. If D is a factor of n, then all the factors of D divide n. And the best way for me to show you what that truly means is by example 3, which will end this second video of this lesson. So here's what this means. If 24 divides some number, and I don't even know what that number is, if 24 divides some number n, then all the factors of 24 would also divide that number. And so if this particular number is divisible by 24, then that number is also divisible by every factor of 24, which is what this is saying up here. So what is 24? What are the factors of 24? 24 is divisible by 1, it's divisible by 2, by 3, by 4, by 6, by 8, by 12, and by 24. So if this particular number n is divisible by 24, then it's also divisible by all of these numbers as well.